Have you ever looked around you and just wondered, why is there all this stuff? It's a simple question, but honestly, it's one of the most profound you can ask. Look at your hand. Feel the chair you're sitting on. Gaze up at the sky filled with clouds, stars, and galaxies. All of it is here. All of it exists. But according to our best understanding of the universe's beginning, none of it should be. The very fact that you are here, reading these words, is a cosmic anomaly. To understand this cosmic puzzle, we first need to get to know the main characters, matter and antimatter. Think of them as identical twins with one crucial difference. Matter is the familiar sibling. It has a positive charge in its atomic nucleus, protons, and a negative charge in the electrons that orbit it. It has mass, it takes up space, and it builds the world we know. Antimatter is the elusive, mysterious twin. Every particle of matter has an antimatter counterpart. An electron, with its negative charge, has an anti-electron called a positron, which is identical in every way except it has a positive charge. You could have an anti-atom with a positron orbiting an anti-proton to make anti-hydrogen. The moment matter and antimatter meet, they annihilate. They don't just collide, they utterly destroy each other, vanishing in a burst of pure energy. A single gram of antimatter meeting a gram of matter would release as much energy as a large nuclear bomb. If the Big Bang produced matter and antimatter in perfect balance, they should have been intimately mixed in the hot, dense soup of the early universe. The result would have been a cosmic-scale demolition derby, a frenzy of annihilation that left no survivors. The universe would have become a vast, empty, and rather boring place, filled only with a diffuse glow of leftover energy. For every billion pairs of matter and antimatter particles created, there was just one extra matter particle left over. That lone survivor, the 1 in a billion left over, is what went on to form everything. Every star, every planet, and every living being is a descendant of that tiny fraction of original matter that escaped annihilation. When we look out into the cosmos, we see a universe that appears to be made exclusively of matter. If a galaxy made of antimatter were to collide with a galaxy made of matter, it would produce a spectacular display of gamma rays from the annihilation along their boundary. We have never observed such a signature. The absence of antimatter is as big a puzzle as the presence of matter. In 1967, the brilliant Soviet physicist and dissident Andrei Sakharov considered this very problem. He didn't just point out the puzzle, he laid out a clear set of ingredients needed to cook up a universe like ours. These three conditions have become the essential checklist for any theory attempting to explain our existence. They are now famously known as the Sakharov conditions. The first condition is perhaps the most radical. Sakharov stated that a process must exist that violates something called baryon number conservation. Baryon number is just a way of keeping score. Give every proton and neutron a score of +1, and every antiproton and antineutron a score of -1. Sakharov argued this rule must be breakable, allowing for the creation of more baryons than antibaryons. The second condition introduces an even deeper level of unfairness. Sakharov said that the universe must violate two fundamental symmetries known as charge conjugation, or C-symmetry, and the combination of charge and parity, or CP symmetry. To get a surplus, the rules themselves must have a built-in bias. The final ingredient in Sakharov's recipe is a departure from thermal equilibrium. This rapid cooling would effectively freeze in the matter surplus before the universe could smooth it out again. The rapid expansion locked in the asymmetry, making it a permanent feature of our cosmos. This is the principle behind experiments like the Super Kamiokande or Super K detector in Japan. Deep underground, in a repurposed mine to shield it from distracting cosmic rays, sits a colossal tank. This tank is filled with 50,000 tons of ultra-pure water. These electronic eyes stare inward into the pristine darkness of the water, waiting patiently for a tiny, telltale flash of light. They are hunting for the ghost of a dying proton. While some scientists look for decaying protons deep underground, others are busy recreating the conditions of the early universe right here on Earth. This is the world of particle accelerators, colossal machines designed to smash particles together at nearly the speed of light. The accelerator smashes protons together, creating a shower of exotic particles, including B mesons, which contain a beauty quark, and their anti-B mesons. With the known quarks failing to provide enough CP violation, the spotlight has turned to one of the most mysterious and elusive particles in the universe, the neutrino. The game-changing discovery was that neutrinos can change their flavor. As they travel through space, they can spontaneously morph from one type into another in a process called neutrino oscillation. This is exactly what experiments like T2K, Tokai to Kamioka in Japan are designed to test. While particle experiments probe the rules of the universe on the smallest scales, cosmologists are looking for clues on the largest possible scale. Their evidence comes from the oldest light in the universe, the cosmic microwave background, or CMB. The CMB is the faint afterglow of the Big Bang, a sea of microwave radiation that fills all of space. The map shows that the CMB is not perfectly uniform. It has these tiny temperature fluctuations, hot and cold spots that correspond to slight variations in the density of the primordial soup. These tiny variations are the seeds from which all future structures, like galaxies and galaxy clusters, would eventually grow. By studying the statistical properties of these spots, cosmologists can test their models of the early universe and constrain the parameters that define our cosmos. It tells us exactly how much ordinary matter exists in the universe, confirming that it makes up only about 5% of the total energy and mass of the cosmos. Despite all the incredible progress, the stark reality is that the mystery of matter's dominance is far from solved. When physicists plug this known amount of CP violation into their cosmological models, the number that comes out is far too small. The predicted surplus of matter is about 1 billion times less than what we actually observe. It's like trying to fill an ocean with a teaspoon. The known sources of asymmetry are simply not potent enough to explain the sheer existence of the galaxies around us. The pieces of the puzzle are on the table, but they don't seem to fit together correctly. This leaves us in a challenging but exciting position. The story of our creation has missing chapters. The fact that our current theories cannot explain our own existence is not a failure but a powerful signpost. It points toward a deeper, more fundamental reality that we have not yet uncovered. The inability of the Standard Model to explain the matter-antimatter imbalance is one of the strongest pieces of evidence that it is not the final theory of everything. One popular class of theories is known as supersymmetry, or SUSY. Supersymmetry proposes a radical new symmetry in nature, suggesting that every known particle has a heavier superpartner. Another compelling idea, known as leptogenesis, shifts the blame away from the quarks and onto the neutrinos. The next generation of experiments is poised to push the boundaries of our knowledge even further. The high-luminosity Large Hadron Collider will increase the rate of collisions. Massive new experiments like the Deep Underground Neutrino Experiment represent our best hope for a definitive answer. On the cosmological front, new telescopes and observatories will continue to map the universe with ever greater detail. The profound implication of this entire mystery is that our existence appears to hinge on a series of cosmic coincidences. It seems our cosmos is exquisitely fine-tuned for existence. In this view, there may be a vast multiverse of other universes, each with slightly different laws of physics. We naturally inhabit one of the rare ones where the conditions were just right for matter to win and for life to emerge. This cosmic perspective can foster a sense of wonder and humility, connecting us to the grand, ongoing story of creation. We are not just inhabitants of a random universe, but survivors of a cosmic lottery of unimaginable odds. Every atom in your body is a survivor of that initial cosmic imbalance. Our entire universe, in a very real sense, is just the cosmic rounding error. It's the scrap heap of a far grander battle between matter and antimatter. The 1 in a billion surplus that led to our existence highlights the fragility and preciousness of a universe filled with structure and life. Ultimately, solving the mystery of matter's dominance is about more than just filling a gap in our theories. It's about reading the first page of the cosmic history book. It connects the world of subatomic particles to the grand sweep of cosmic evolution. Finding the answer would give us a complete narrative of how the universe went from a point of infinite potential to the rich, complex, and matter-filled home we know today. The search continues, driven by the simple, powerful, and deeply human question: why are we here? We may be the generation that finally learns the full story of the great cosmic vanishing act, and in doing so, truly understands why we are here in a universe of something rather than nothing. So we have our two main characters, matter and its mirror twin, antimatter. Now let's travel back in time, way back, to the very first moments of the universe.